So I hope you can see the potential benefit. Watch my video that covers the quick access toolbar, but I'm going to click this button here.
Sir, shall I start the session?
Yes,
Hello,
sir.
sir.
Okay. Okay, sir.
Okay, fine. Thank you, sir. So, good afternoon, all the participants. Today is day 5 of this FDP, and we are now here to quickly understand the concepts of decision tree, bagging, and boosting techniques. Right, these bagging and boosting techniques are part of ensemble methods. So, quickly we go through first what is meant by decision tree, and then from how we will move from decision tree to random forest, and what is the requirement to move from single decision tree to random forest. And once we understand that concept, and in under which particular category the decision tree falls, and what are those categories like bagging and boosting, and then we will quickly see around 10 to 15 minutes from now, and then we will immediately switch on ourselves to lab session, right? So, these are the topics that we will cover today. So quickly, first we go to decision tree, right? Fine. So coming to the concept of decision tree. Decision tree is one of the supervised machine learning algorithms, which I have postponed to discuss in this session, because this is the fundamental or foundational supervised learning algorithm for the concept of bagging and boosting. So for that reason, I have postponed this decision tree to today's session. Fine. So what is a decision tree? A decision tree is a tree-like graph where each node represents a decision, right? What is a decision? A decision is nothing but the uh, uh, it could be a class label, or it could be another attribute, because if it is a class label, it means the the test on a particular attribute has shown or has given us what is called as pure class labels. So what is meant by pure class labels? There is no distribution with respect to the mapping between feature and the class label outcome, right? So if, let us say, if I take the example of color of a eye color of a person. So if I have 10 records, all these 10 records are different, having different colors, different eye colors, but all these different eye colors are mapping to a single what you say outcome called yes, let us say, right? So it means then the outcome from that particular test is nothing but the class label. Sometimes there will be a decision, not sometimes, strictly speaking, in real time, in real world problems, most of the times we have what is called as distribution of class labels across multiple values, right? Or yes, across multiple instances, right? So, and this distribution will be in such a way that uh, if you consider the sample data, in that sample data itself, these class labels will get distributed. That means in the, if I take the same example of 10 attribute data, for these 10 attributes, there might be two outcomes distributed across these 10 attribute instances, 10 attribute values, right? Like in the sense, yes for 4 records, no for 6 records. So this is said to be impure. So during classification, what happens is, or during decision tree learning, what happens is, if the algorithm encounters this impurity or distribution in the labels, then what it does is it goes for another check on another attribute. So if that check on another attribute leads to clear classification of these records, in the sense all the 4 can be classified at on one side and all the 6 can be classified on the other side, then it will classify and show us the outcomes as the decisions, right? So at any point in time during the learning process of the decision tree, you may encounter either a class label or another attribute, right? So that is what is given here. But finally, at the last level of the decision tree, all the nodes in the last level will be the decision nodes, will be the class labels, right? So how the decision tree looks like. So before seeing this scenario, first see how a decision tree looks like. So this is the decision tree. Initially, in order to learn the decision tree should start with a attribute, right? So from among list of available attributes, the algorithm need to select an attribute to start with, right? For growing the decision tree, right? Among all the attributes, how the algorithm chooses the best attribute to start the decision tree training process or growing process. So there are techniques for selecting the attribute. So like you are seeing the Gini value here, Gini value or GINA Gini value. So according to this Gini value, uh, uh, for which particular attribute the Gini value is, let us say, less, right? Gini value is less. Uh, then that particular attribute is chosen by the algorithm and starts growing the decision tree, right? So now let us say if there are 5 attributes, one attribute has got some Gini value like this. So I don't take the attribute name density because I haven't, I'm not talking about scenario. As of now, you please understand that some attribute has been selected based on this Gini value. Now you see there are 7 samples satisfying this particular attribute, or 7 rows records from the data sets satisfying this particular condition, attribute condition. Now these 7 are actually distributed across what you say, these 7 are actually in this fashion, distributed in this fashion, 1 2 4, right? 1 2 4. And the class label is actually what is say confusing here. Initially, the class label is said to be plastic, but there are some other records, right? There are some other records which are not actually plastic. So that's why. So as the class label got distributed, so how many class label values are there? There is plastic, there is aluminum, there is steel, right? So from among these values, let us say this particular value has got the class label for these 2 records. The class label is actually aluminum, but not plastic, right? So among 7, 5 records has the class label as plastic. Remaining 2 records has got the class label aluminum. So that means there is a distribution here. So further, we need the algorithm does a test. So does a test, and this test has revealed that uh, if you can classify these 2 records clearly with the class aluminum, then there is no need to once again generate a new test on the attribute, right? So this test, what happened, to the right side another attribute has been chosen by the algorithm. Now please understand, whenever the algorithm goes to the next level, and in that next level, if the attribute is chosen instead of class label information, the attribute is chosen in such a way that uh, the it is chosen on based on the subset of records but not on the entire data. So earlier in the first level, how many records have been already tested? 7 records have already been tested. So from let us say if there are 30 records, out of 30 records 7 are already tested. So those 7 records and this attribute will be kept aside, right? 7 records and this attribute will be kept aside because already the test has been already conducted on that attribute. So now how many records are available? Remaining 23, right? Let us say 23 records are available, and this density and the 7 samples are kept aside, and the remaining attributes will now get tested. So among 5 attributes, all the density is gone. So there, let us say there are remaining 4 attributes in which there is another attribute called cost per unit volume, right? So this attribute has been tested here, and this attribute is chosen by the algorithm based on the Gini index, right? From among 23 examples and 4 attributes, right? From among 23 examples and 4 attributes, this attribute has been selected. Now, this attribute for the available class labels, if you have, there are only 5 samples, and these 5 samples are like this, right? So these 5 samples contain all the class label to be plastic, right? All the class label to be plastic in this particular attribute selection. But still, if you see carefully, there is one record whose class label seem to be steel, right? One record whose class level seem to be steel. So that's why this particular what you say 5 records are once again further classified for other class labels. So in order to make the entire what you say classification pure for that attribute, so cost per unit volume, if it is less than or equal to 3 uh, for 4 samples, the class label is plastic. If it is greater than 3, then there is only one sample whose class label is steel, right? Here also, if density is less than or equal to 7.5, there are two labels whose class label is aluminum, right? If density is greater than 7.5, then still there is another attribute to be checked in order to further classify the material surface, right? Further classify the material type of the material, right? It could so that has led to what is called as cost per unit volume, right? Any doubts here? Any doubts? So like this, the decision tree, what you said, generation will get terminated only when all the records have been used in the training process from the data set, or all the attributes have been tested, whichever completes first. Accordingly, the decision tree training will get terminated. Any doubts here? Participants, if you have any doubts, you can unmute yourself or you can type it in the chat box. So there are various ways to select the attributes: Gini index, gain ratio, what you say, entropy. So these are the various measures that you can actually calculate on the attributes. And among these things, if the values are, if any particular, if the measure is less for any attribute, so select that attribute for the tree growing process, right? Fine. Now going back to the scenario. So the scenario considered for decision tree is material selection for structural components, right? So which particular material is to be selected for the given task, right? For the given chosen application or for given task. So which material is to be selected? And how do you select the materials? So on what basis you will select the materials? So I request participants to answer this question.
Santosh sir, there is one question in the chat box.
Yes, sir.
Third box.
Okay, sir, in this image, how the Butler attribute satisfy the properties and give that this is this and give that this for that solution, how the decision is happen in this event, right? So see here, the doubt raised was how that attribute satisfy the properties. That's what there will be a counting process that actually internally happens. So whenever you are in the process of selecting an attribute using any particular measure, what happens is you will actually count the mapping between the attribute value and the corresponding class label value. So how many attributes, let us say if I take the what you say uh, density, or let us say uh, the loan uh, total income of a particular in a loan decision process, the attribute could be total income of a person, right? Total income of a person. There are three values, like discrete values. Let us say it is low, medium, high. Total income is low, medium, high. So now what happens is, in the as now I have selected the attribute to test for the sake of selection, attribute selection process to grow the tree. uh, Now what happens is, for low, how many values are there for the attribute at total income, how many times this low has been repeated. So you count, right? And how many times medium has been repeated, how many times high has been repeated, right? In the given set of in the given training set. Now let us say if there are 20 records, so low let us say low has been repeated 5 times, uh, medium has been repeated for 10 times, and high has been repeated for 5 times, right? Now this counting has been done, right? Now what happens is, for this low, for this set of 5 low values for that attribute, uh, how many low are associated with the loan decision yes, and how many low are associated with the loan decision no, right? Are you getting my point? Yes, any doubts?
No,
Now
sir.
right, now in the same lines, for a medium also, how many medium instances are associated with the class label yes and no, and for high also association with class label yes and no. Now like this, what happens is, the attribute selection measure like Gini index, gain ratio, or entropy calculates these counts and provides them in terms of probabilities, right? And it has certain formulae in which these probabilities are plugged in, and based on these based on that formula, it returns what is called as information. It returns what is called as information. So that is what measured in terms of bits actually, right? As Shannon is one of the computer scientists who has proposed the concept of information theory, and he said so entropy or impurity can be measured in terms of bits. So here impurity or entropy, when you are calculating uh, this distribution what you have seen earlier, right? Like low, how many low are associated with this and how many low are associated with no. Now this distribution actually in the mapping process, if you see all the 5 low instances are mapped to only s, that means there is no impurity. But as the low values have been already mapped, some of the low values are mapped with s and some are mapped with no, that raises what is called as impurity or entropy, right? So we should calculate that entropy or impurity, and based on that we need to come to a particular information gain or gain ratio or Gini index, and we should finalize upon which particular attribute is to be selected based on the evaluation criteria of that particular measure. Any doubts? Okay, now so we quickly go back to the uh, I have asked a question earlier. The question was on what basis engineers, mechanical engineers will select the materials, right? What are the characteristics? What are material characteristics, or on what basis you will select the materials for a given application? So please answer in the chat box. The choice of material, as you see, the choice of material depends on various factors as given here, like tensile strength, elasticity. These factors are the mechanical properties here. Not only these tensile strength and elasticity are taken into consideration, but also cost, environmental impact, right? And other factors are also important to assess the choice of the material, right? So now these are the attributes that go into the decision making process, right? As you have seen in the decision tree, that not only these attributes, but also what are the other attributes that you have seen? Density you have seen, right? And other thing what you have seen, cost per unit volume also you have seen.
Sir, the chat box, answers are there, sir.
So
Chat
strength,
box.
yes, sir, yes, sir. So the answers are like the strength, stiffness, toughness, right? Thermal property, strength, roughness, toughness, right? So these are the various what to say factors with which material can be chosen correctly, right? So according to the load capacity, right? All these things, right? You, as you have said, these are the important attributes, right? So now with these attributes, for these attributes we actually collect the data, and we finally provide a class label, say that based on this set of values for these attributes, the material that is to be chosen is some like plastic or steel or aluminum, right? So you have the range of values for each particular attribute, and those values you need to get it by the specifications of the by from the specification of the material, or by the let us say any in general you will get it from the specification of the material, right? So or based on the task at hand, you will you need to identify what kind of values we need to actually come up with, right? So in order to assist the mechanical engineers to identify the material, appropriate material, decision tree algorithm can be chosen, right? So the what is it, the best part of decision tree algorithm is it is robust to noise in the data. So if there is some what is a class label mismatch, if a particular person slightly modifies the class label in the data set, still the decision tree able to withstand with that particular noise and come up with a most relevant solution, right? So you see this is the trained decision tree as you are seeing into the right side. So clearly these are the class labels, right? This is the leaf node. These two are also the leaf nodes, right? The leaf nodes are informing you the class labels, right? If this is the case, right, I can view this as a rule from top to down. So what is the rule here? If density is less than or equal to 7.5 and cost per unit volume is less than or equal to 3, then the material that you need to select is plastic, right? If density is less than or equal to 7.5 and cost per unit volume is greater than 3, then you should select the class label material is selected is steel, right? This is the way we can actually form rules also, right? So while forming the rules, the order in which the rules are generated is, so we start from top node, root node, and we come down and we move in the left to right direction to form the rules, right? So this is the way first we come and we generate a first rule, and this is the way we move in the right side and we generate the second rule. So here also we have another material selection rule, that is if density is greater than less than equal to 7.5, then the class you are selecting is aluminum. Right? Any doubts here? Yes. Right.
Yeah, you can continue, sir.
Okay. So now, like this, what we do is we actually form decision trees. Now from decision trees, we are actually moving to random forests. So what is the reason to progress towards random forests is, you in many of the industrial applications and real-time applications, uh, in order to form a, uh, a high, what is a good model or great model, let us say, a robust model, strictly speaking robust model, industries require robust model. So in order to generate a robust model, it is not possible to only depend on rely on only single decision tree. Rather, they would like to have a collection of decision trees, right, whose accuracies can be either averaged or voted for majority values, and come up with a unified model kind of thing, right? So from single model to a unified model, that the requirement was there for the industries. So thereby what happened is they have come up with a concept called bagging, right? Ensembling, the actual term that we need to use here is ensembling, right? What is meant by ensembling? Ensembling means collecting the decision trees, or let us say collecting the group of models, and making these models combined together in the form of either average of the accuracies of all the models, or majority voting of the of across all the models, and give the final decision, right? So this is nothing but ensembling, and what the specific technique that I am talking here is bagging, right? The name of the algorithm is bagging, that I have explained now, right? So there is another kind of ensembling called boosting, right? What is the difference between bagging and boosting? We'll quickly come to know now, right? Now, so first of all, we go to bagging, right? So before seeing bagging and boosting, just we see the how the out how the output obtained in bagging and boosting techniques, right? So bagging is an acronym for the name for the algorithm bootstrap aggregation algorithm, right? So now what is happening in bagging? So you are collecting, you have divided the entire data into two parts, training and testing. So the training part of the data is sampled in the random fashion, right? If you have 100 records, let us say, these 100 records are sampled in the random fashion with replacement. So sampling with replacement, what do you mean by sampling with replacement? Whenever a particular instance is taken for the sake of creating sample, that instance is present in the sample. Once the sample is generated, once again that instance is replay is kept back to the original training data. So that what happens is, there will be reuse of the same instance across all the samples. So this enables the model this enables the individual model, right, to find to find diversity in its particular learning process, right? Whenever a model is there, what happens is you are doing random sampling, and you are replacing the records, right? Certain portion of the records. What then this leads to uh, learning a model that is more diverse, because it has good number of patterns, right? And these good number of patterns account for what you say good accuracies, right? So like this, in this diagram you are seeing there are three models, right? Each model has got its own accuracy, right? Its own accuracies. Now what you are doing is, you are taking up all these three models and you are aggregating, right? Or aggregating or finding the majority vote. Now majority voting says among these three models, how many models have got or which model has got highest accuracy, right? So if there are, let us say there will be so many cases where in one of the cases is in among three models, two models are having same accuracy and third model having less accuracy. So then majority voting says you go with the accuracy of those two models because it is higher than the third model, right? So I am only talking about one such case, right? So that is a majority voting. And in aggregation, what happens is you are simply averaging all the accuracies across these three models and finally forming a final classifier, final model whose accuracy is high. Understood? This is bagging. Now coming to the other form of ensemble learning, that is boosting. In boosting, what is happening is the boosting works in this fashion. What it does is it it instead of sampling the data in the random fashion, it samples the data in the sequential manner. So what do you mean by sequential sampling? So if there are 100 records and here you are seeing three iterations, right? Let us say three models, strictly speaking here also three models. In one iteration you will get one model, right? I will check the chat box later. Now if you see in one iteration you are having one model, and this model has first let us say 33 records. First model has got the first 33 records. In iteration 2 we got another model, and this another model actually depends on the previous model. How it depends on the previous model? This iteration 2 contains a new model that has two things. The first thing is it is dependent on the first model in terms of the weightage on the number of misclassifications, right? So how many examples have got misclassified in this first iteration? You see there are three examples. Let three positive examples have got misclassified under the region negative examples, right? Now in iteration 2 what happens is the boosting algorithm gives weightage those three misclassified examples in such a way that these misclassified examples will get correctly classified. During this weightage specification process, what happens is some of the already correctly classified examples may get once again misclassified, right? Now you see, now boundary has been improved. The decision boundary, the linear separator, has been moved to the right side. Now, because of moving to the right side, the three misclassified examples have come into the correct classification range. Yeah, now the correctly classified examples got misclassified. Now what happens? The algorithm once again adds weightage to these misclassified examples and tries to learn a boundary, right? Which accounts for correct classification of these three misclassified records. But still during this process what happened, two positive examples got misclassified and one negative example got misclassified, right? And if your boosting algorithm according to the number of iterations that you specify cannot classify clearly all the positive and negative examples, finally what happens is the boosting algorithm does form a way, right? Form a way to generate the the piecewise decisions, right? These are known as piecewise decisions, right? In this is one piece in which these are positively classified. This is another piece positively classified. This is a positively classified positive region in which there are no examples present, and this is another piece containing negative example correctly classified. Like this, you see, this is said to be a strong classifier. Until the examples are not correctly classified by the model, that model is said to be a weak classifier. Understood? So by considering all these weak classifiers, this boosting algorithm, what it does is it forms a piecewise linear classification model and finally forming a strong classifier. Any doubts, sir? 190. So any doubts with respect to this discussion? Yes. So here the most important thing is the sampling occurs in the sequential manner in boosting, whereas in bagging the sample happens in the random fashion with replacement. Right now what we do is we quickly go to the scenarios. Before that, we need to know what are the algorithms under bagging and boosting. In bagging, we have random forest, bagged decision trees, bagged kernel. In boosting, we have ADA boost, gradient boosting, stochastic gradient boosting. And in this discussion, we only concentrate on random forest and ADA boost, right? So yes, so from decision tree, you are moving towards random forest. So as I told you, random forest is nothing but a bagging algorithm in which we have collection of decision trees forming a forest, right? Forming a forest, and these collection of decision trees will provide a robust model, right? So this a random forest can be used for classification and regression. Now, what is the scenario that is considered as optimizing the performance of a new engine? Prototype, right? So any engine has got certain attributes, characteristics like this. If you see, the characteristics are exhaust system characteristics, compression ratio, air fuel mixture, fuel injection timing. So these have got standard operating values, right? And we have this the advantage of using either decision tree or random forest is these will help you to identify the important features in the top down approach. So starting from the root node to the nodes, one level up in the tree, the attributes are considered in the sort in the descending order, in the on the base of its the importance, right? So the root attribute has got highest importance, and the attributes in the below have got least importance, right? Like this, you can select the important attributes, and by considering that attribute, you can form a random forest like this. So this is the learned random forest, right? I think all the people are able to see here, right? So a big random forest has got learned, right? Now what we do is we'll see the scenario for bagging specifically. This is accurate and stable prediction of quality of each manufactured turbine blade. So now I think you people know this scenario in terms of mechanical, what is it, as you are from mechanical domain, I think you people know about the turbine blade manufacturing and its what you say, and its quality, right? So quality prediction, right? So there are attributes like what is say variability, including material variations, temperature fluctuations, machine tolerances. So in the manufacturing process, there will be the variations with respect to these attribute values. We should consider these values and generate a bootstrapping model, right? So the model, right, if you see, these are the two what is say models. In bagging, we generate some k models according to our requirement, and these k models, uh, what we are doing is we are integrating these k models on the basis of either accurate aggregation or voting, and finally forming a accuracy, right? So this purely is based on the data that is generated in the synthetic form. Right now, coming to the boosting technique. In boosting, we are taking the scenario of a robust and accurate simulation model for predicting the structural integrity of a bridge under varying load conditions. This is it involves what are the factors like material properties, environmental conditions, geometric specifications, right? So these are the factors that we consider. And now the accuracy of your current model is not meeting the desired performance standards. If this is the case, then if you want to improve the performance of your current model for this particular scenario, you are using boosting technique to do that, right? If you consider boosting technique, now how the what is how the weak learners will be, you see like this. So there are 6 weak learners on the particular data, right? Load condition data, bridge load condition load prediction data. So these are 6 weak learners that you are seeing. So in each learner, if you see in each weak learner, there is some amount of misclassification here, you see. So there are 2 to 3 examples that are misclassified, and 2 examples are lying on the boundary of the decision tree. In weak learner 2, what happens is this separator has been moved towards the left to some extent. Now this change in the linear separation has account for 5 examples getting misclassified, positive examples, right? And now based on this weak learner 3, right, and each weak learner is dependent on a particular sequential sample, right? So the sequential sampling and the concentration on the previous misclassified records is actually happening here, right? Now in weak learner 3, there are once again 3 records got misclassified here, right? In weak learner 4, now what happened? Weak learner 4 also more number of negative records got misclassified. In weak learner 5, still negative records got misclassified. And weak learner 6, as comparatively speaking, weak learner 1, weak learner 2, and weak learner 6 are somewhat better. So because of these 3 weak learners, among all the 6 weak learners, we are able to see the accuracy around 48%, right? So just by boost, by doing the boosting process, so it could be like averaging across all the uh, model accuracies to find the final accuracy of the strong model. The strong model accuracy is now 48%. Just to this, with this you should make you understand that the weak learners accuracies are less than the accuracy of the final model, final boosted model, right? Any doubts with respect to this? So now with this, we are now ready to understand the, see, what you say, demos. We quickly go through these demos, right? I will once again come back to the demos now. So I would like to inform all the participants to open their Colab environments and upload the decision tree Python notebook, right? Right. So what I am doing is I have uploaded my decision tree model, right? Uh, this particular Python notebook doesn't need any data set to be included because
Please
data.
share your
Yes, sir. Yes, sir.
Sir,
screen. Thank
Sorry,
you.
sorry. I am sharing the screen. Fine, fine. So is the screen visible, sir, now?
yes,
Yes.
sir.
Thank you, thank you. So and now you see, I think you people are now at this location, at this screen, right? This screen contains the decision tree Python notebook file. And in this, what I am doing is I am importing decision tree classifier class from the sklearn.tree submodule as sklearn.tree package. Right. I am also importing accuracy scores and classification reports from the sklearn metrics. Right. From sklearn model selection, what I am doing is I am importing train test split. This is a must when you are working when you're doing when you're performing machine learning task, right? So you need to split the data into 2 parts, training and testing parts, right? And you are using pandas library to hold your data from external environment into the Python environment, right? Now the data has been considered in the synthetic manner like this: material selection data. These are the attributes collected: tensile strength, density, cost per unit volume, and the class label is recommended material. Right. So now, how many records we have considered? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 records we have been considered. Across these 10 records, you are seeing 10 class labels, right? Distributed. across these 10 records, right? The data itself is very much clear that there is impurity in the data, in the sense the class label got distributed, that different class labels are there, and they have got distributed across the records, 10 records. So now what you are doing is you are creating the data in terms of x and y, as we have already seen, in terms of features and targets, right? Now once you have created x and y, now you are using the model, you are using the method train test split to divide the data into two parts, training and testing. And the test size is 30% of your data, right? That means 3 records will go into testing, right? From the 10 records, right? Right. Now in order to stabilize the data, we are using random state equal to 42, right? And now what you're doing is you are creating a decision tree classifier. Actually, if you see, if I place the cursor here, now what happens, you see, uh, it need to show up what are all the hyperparameters included in the decision tree, right? So are the as you are seeing, these are the various hyperparameters for the decision tree algorithm. So minimum sample leaves is the by default the value is 1. Minimum sample splits should be 2 for the decision tree. These are the values that you can configure, you can modify at any point in time, right? And what you are doing is maximum leaf nodes are any, you are specifying, and you can have n number of leaf nodes, right? And impurity decrease, minimum impurity decrease value is 0. It means, what do you mean by this? So there should be no impurity in the tree classification process. That means the all the records must be clearly classified, right? The And you are selecting the splitter attribute splitting mechanism to be best, right? So like this, what you are doing is you can modify these hyperparameters, and accordingly what happens is, when you specify your own hyperparameters, then your model is said to be biased, right? As I told you in the supervised learning concept itself, when you set hyperparameters, configure your hyperparameters as per your need, it leads to what is called as bias in the model. So whenever you are including more number of hyperparameters configured, it leads to high bias. So high bias will account for low variance. So that means decision tree will work fine for on the training portion of the data. We need to check whether it is working, it will work fine for test portion of the data. So there are various things how to handle the over fitted decision tree, which is not our part of the discussion as of now. So if you see, you are fitting the decision tree here, on the trained portion of the data. So once you fit a decision tree on the trained portion of the data, this is a visual model. Please try to understand. Naive Bayes is a mathematical model, and this is a visual model, right? Models can be of two types: visual model and non-visual model, and this is a visual model. Right. Now once you got the model, you can call predict method to test on the test portion of the data, right? And once you got predictions, you can actually calculate the accuracy on the test portion of the data. And that accuracy, with that accuracy, you can form the classification report, because the precision, recall, and f score can be generated, right, from this particular accuracies, right? So it has its own what to say, values for the true value, true positives, false negatives, and so on, right? now Now what you are doing, in order to predict on the unseen data, you are specifying particular values, right? For the tensile strength is 420, density is 7.5, and cost per unit volume is 2, right? If you substitute these values in this tree, now what is the class label assigned? We can come to know. Now tensile strength is 420. Is that attribute there here? No. So the first attribute considered is density. Now what is the density value considered? 7.5, right? So if density value is less than or equal to 7.5, yes, density is equal to 7.5, yes, this attribute is considered. And what is the next attribute? Cost per unit volume is 2, and cost per unit volume is less than or equal to 3, right? Here already density attribute has been satisfied, and it coming to this, and cost per unit volume is less than or equal to 3 means the value given is 2, which is less than 3. Obviously, as these two are satisfying, it goes to provide this class label. What is the class label for the test attribute? Plastic. Any doubts? So if I run this, you are able to see this message also, right? I will run this code once again so that you will come to know. Right. So now it has the code has got executed, and it is recommending the class label to be what? Plastic. Right. It has recommended the class label as plastic, and the accuracy is 33.3 here. Right now. Now you for the sake of visualizing this decision tree, what you are using is the method. You are calling the method plot tree from sklearn tree, and you are using this method in order to define your attributes, right, and corresponding attribute values. So obviously it shows it plots the decision tree in this manner. Any doubts? Any doubts, participants? Okay. Now we will quickly go to the next one, that is random forest. Right now, we'll upload. Before that, I will stop this session. RAM and disk, right? So fine. Now file upload. So we'll select random forest model, right? So yes, so this is a implementation of random forest algorithm, that too specifically, as I told you, random forest can be used for both classification and regression. We are using the regressor model because this particular scenario is actually the suitable supervised learning category is regression. Why? Because the data is in terms of continuous values, and there is a dependency here, right? There is dependency on what is called as the what is a the target is horsepower, right? You are using the target as horsepower. There is a dependency on the attributes fuel injection timing, compression ratio, and air fuel mixture like this. uh, those are influencing the horsepower. So that is better understood with the help of regression model, right? So it is multiple regression, and that multiple regression model is used in the form of random forest, right? So now you see we are using this multiple regression model for random forest, and what we are doing is we are specifying the data here itself for each attribute, and we are splitting the data. Now we are considering the test size to be 20%, and we are stabilizing the data, and we are estimating the number of decision trees to be learned to be 100. So this is the hyperparameter for random forest regressor. One of the hyperparameters is the number of estimators. So how many trees you would like to see in the random forest? So you are specifying it as 100. So you can modify this value accordingly. So I would like to see only 30. Let us say I convert this to 30. So 30, and now I am fitting the model, and I am going for predictions, right? So as it is a regression model, what I can do is I can have the model performance on the test portion of data in the form of the cost function, which is mean square error. So I am using this mean square error method. So this mean square error comes from scalar metrics. So I'm using this mean square error method, and I'm getting the MSC value, and I am plotting the important features, and what I am doing is I am showing up the decision tree like this, right? So what I am doing is I am simply running here, and please understand I am changing the number of estimators in the random forest, number of decision trees that you see in the random forest to be 30, not 100. Just see, I will run this code. Now you see the size of the tree has got reduced, right? Also, you are able to see the important features. The highest feature being exhaust system characteristics. Next important feature is compression ratio, and then air fuel mixture and fuel injection timing. The most important feature influencing the horsepower is exhaust system characteristics. And the next one is compression ratio. Next is air fuel mixture value. And the least among these attributes that is influencing the horsepower is fuel injection timing, right? So uh, these all four are actually influencing the horsepower, but among these four, which is the highest one we are seeing here, right? Any doubts? Any doubts with respect to this? Right, if you see, you can count the number of trees also here. So if you want to be more simple, if you want to simplify more, you can just see for 10, so that it will be clear, that the random forest will be clear, right? So of course we haven't executed this, we need to execute this. We need to execute this and see the model. So if for 10 trees, how the random forest looks like. We haven't executed earlier, right? Now we are executing this now for 10 trees. But if you see, the MSC value has been increased, right? MSC is high if I reduce the number of trees in the random forest, right? So to make the model more robust, you should not reduce the number of estimators like this. So a more robust model will contain more number of decision trees. The size of the forest should be high. Did you understand my point, right? So this is 1, 2, 3, 4, 5, 6, right? 7, 8, and then we have 9, and further it could be somewhere here internally, it could be some 10, 10. Finally, we have 10, right? So don't go for sub branching. Only you see the levels where further branching is done at the next level, right? Right. So any doubts? Okay. So if you want to see the bagging and boosting, now quickly, if you want to see the code, I will just load them up also, because we still have 5 minutes of time. So better I will load, right? Bagging classifier, right? Bagging classifier, you see decision tree for bagging classifier, and boundaries, right? You are seeing the decision boundaries also, right? Now now we want to see the bagging classifier, and we would like to see the boundaries here. So just I'm using the bagging classifier and in from Ensemble, and I would like to see the results here, right? So in terms of decision boundaries, so as you see, decision boundaries generated here, right? Now you see, in bagging, we got two models. In the first model, with random sampling with replacement, three examples got misclassified. In the second model also, three examples got misclassified. So the individual accuracy of these models have got aggregated, right? These got aggregated, and these aggregated models are accurate as shown for accuracy here, right? So it is 49.5% accurate. The model accuracy is 49.5%, right? So internals of this bagging classifier is understood in terms of its hyperparameters. So if I simply put a cursor and see what are the hyperparameters. So bootstrap is true. Without bootstrapping value true, it is not possible to find the random samples with replacement. And base estimator is deprecated. This attribute value is deprecated, and number of estimators you are performing is actually 10 default value, right? Right here you have modified that value to 50, right? And you are using base classifier, right? What is the base classifier you are using to find the accuracies of the individual models to generate individual models. That is decision tree. Base classifier is decision tree, and based on each and every decision boundary is the output of this decision tree classifier. This is M1 decision tree model 1. This is decision tree model 2 decision boundaries. Right, you are supplying you are using a base classifier to form a bagging classifier. As I told you, a bagging model is the combination of multiple individual base classifiers. Right, now finally we will see the boosting. Right, now file, upload notebook, and then we see boosting. So this boosting, as we have seen, boosting, it talks about what is saying, giving importance to the misclassified examples from the previous classifier. So, and improving the reducing the error rate in the current iteration on the same, on the base classifier. Right, so you see, you are using here the base classifier is once again decision tree, and on that you are using ADA boost classifier to form ensemble. So ADA boost classifier is coming from SQL and ensemble. Right, and what you are doing is you are uh, generating the decision boundary. Right, so this decision boundary is generated in this fashion. So 6 weak learners have been generated. Now what we are doing is we are running this code to see the output, but still we have the, what is the decision boundaries are shown here. Right, fine, I will run this. Yes, this error is now we are not concentrating on this error because we I would like to see the decision boundaries of all the weak learners. So this is the decision boundary of all the weak learners here, as you see. So this weak learner 1 and weak learner 2 and let us say weak learner 3. In this run, you are seeing weak, 4 weak learners are performing better among the 6 weak learners. Right? Okay. Any doubts? And you would like to find the accuracy of this model. You are simply running this. Right? Now, for the sake of the more accuracy of this boosting model is 48%. Finally, we could able to get the 48% accurate model. Right? After boosting. Now, actually, everything should be there in a single program. Now, I would like to see individually what is actually happening across these things, and accuracy is plotted separately, so that first we concentrate on one thing and then we will see finally the accuracy, how the accuracies look like. So that is why. Right? Any doubts here? So if the participants have no doubts, then we can wind up this session for today, and tomorrow afternoon also we will meet for the lab sessions on ANN, artificial neural network. Right, and a quick look on machine drawing through CNN. Right, machine drawing through CNN, how convolutional neural networks are useful to draw machine drawings. Right, accurately as you see in the AutoCAD. Right, so any doubts regarding this?
And Professor, if they don't have any doubts, we can wind off.
Okay, sir. Okay, so participants, we will wind up the session today, and we will again meet in tomorrow's last session. Okay, tomorrow is the last session, afternoon session. Right, right. Thank you.
Okay, sir. Okay.